Hi everyone, I'm Eric, and today we'll be continuing to learn number theory. And today's topic will be considering congruences, powers, and Fermat's little theorem. Sounds cute, right? Well, it's not as cute as you might think. So first, we'll take a look at the list on the PPT. So let's say P is 3, 5, 7 or prime numbers, and in order to find a pattern, we'll just write P is 3, 5, or 7, and A can be 0, 1, 2 all the way to infinity, but for this table's purpose, it will only reach 6. And some of their powers modulo 3, modulo 5, and modulo 7. Now, the original list is way too big to be actually included in here, so we had simplified this little list. And we see that when it's modulo 3, a squared, whatever a is, except 0 to the nth power is always 0. When it's modulo 3, a squared is always 1. And when it's modulo 5, even though I had simplified it out, a to the 4th power is always 1 as well. And you guys probably guessed it. When it's modulo 7, a to the 6th power, I'm going to write it here because this is when it's modulo 5. It will be 0, 1, 1, 1, 1, 1, 1. So it's all ones. And Fermat also found this pattern. And he thought, can I get a theorem out of this pattern? And this is his little theorem. Let P be a prime number and A will be any number which A and 0 are not congruent modulo P, which basically means that A is not a multiple of P. And also, since P is a prime number, then A cannot divide P. Then a to the p minus 1th power and 1 is congruent to 1 modulo p. And this little theorem, he included it to a letter to a mathematician. But you know what Fermat's like. He doesn't like to write anything except his theorem. So he didn't give a proof to it. And in the end, of course, someone proved it. Leibniz did. And we will be covering how Leibniz had proved his little theorem. But first, since it's a little theorem, then we'll see if it's actually useful. If it's not useful, then why not? We can just skip the proof. And it actually is very useful, and it simplifies computations a lot. Now, if I ask you, what is 2 to the 35th power modulo 7, it's a pure pain to actually calculate 2 to the 35th power, and also divided by 7, which is almost impossible. Calculators might be able to do it, but with the Fermat's little theorem, we can solve this actually quite easily. So we see it's modulo 7, and if you guys don't notice, I'll skip back to the list right here. And a to the 6th power is, except 0, always 1. And with that in mind, we can say that 2 to the 6th power is congruent to 1 modulo 7. Now we don't want to know what 2 to the 6th power modulo 7 is. We want to know what 2 to the 35th power modulo 7 is. So we'll check the connection between 6 and 35, which is just 6 times 5 plus 5. Which means that 2 to the 35th power can be written as 2 to the 6th times 5 plus 5th power. And you can write it as 2 to the 6th power to the 5th power, which is basically exponent multiplication. And multiplication is exponent addition. So times 2 to the 5th power. and it's basically the same as this. So we know what 2 to the 6th power modulo 7 is. It's 1. So we can write it as 2 to the 6th power to the 5th power times 2 to the 5th power is congruent to 1 to the 5th power times 2 to the 5th power, which is also congruent to 2 to the 5th power is 2, 4, 8, 16, 32. So it's also congruent to 32, which is congruent to 4 modulo 7, and it is sure a pain to read, but in the end, we solved this without a calculator exploding. So it actually helps out a lot. So now we'll check the proof. Now, Leibniz didn't think that he would be able to prove it in one big step, so he broke it up into 2 small steps. Actually, one is the main step, and that main step is the first step. So what Leibniz did is he proved that when P is a prime number and A is any number in which this occurs, then the numbers this modulo P and the numbers this modulo P are actually the same, even though they might be in different order. So in order to actually prove this, we're going to see what method we're going to use. So first, we find that all of these numbers modulo P is basically themselves, because no number in this list is greater than P. And also we know that A is not congruent to 0 modulo P, which means that P is also a prime number, so P cannot divide A. So all of these numbers modulo P cannot not modulo P. All of these numbers cannot be divided by P, since we know that when M cannot divide A and M cannot divide B, then M cannot divide A times B, and this is basically the logic behind this stuff. So after we know that, we are only one step away to proving this, which is to prove that there is no repeating modulo P's in this group, or else it will never be the same as this. So what we'll do is we'll get two random numbers from this list, J and K, which satisfies JA is congruent to KA modulo P. And then we subtract both sides by Ka to get Ja minus Ka is congruent to 0 modulo P, which basically means that P divides Ja minus Ka, which we can write it as this in this form. Now, we already know that P cannot divide A, and P is also a prime number, so the theorem from before, where P is a prime number, and when P divides AB, P must divide A or divide P or divide both. It works. So P must divide J minus K. And if that is the case, then it doesn't show anything. Or does it? J and K, they're both smaller than P. So even the absolute value of J minus K, the absolute value of J minus K is at most P minus 2. So they're definitely smaller than P minus 1. And what numbers can divide P when it's still smaller than P? Well, there's only one number that fits, and that number is 0. So then J and K is the same element in this list. And we have finished the proof of this part. And after we did that, it will be very incredibly easy to actually prove the Fermat's little theorem. So this and this are the same modulo P, and this is a condition. So this a times 10 times 3a all the way to p minus a times a is congruent to 1 times 2 times 3 all the way to p minus 1 modulo p. And after we factor out the a, we find that the numbers before a, they're basically 1, 2, 3 all the way to p minus 1, and they're in a multiplication. So we can write it as p minus 1 times p minus 2 all the way to 1, and we write it with an exclamation mark. Now I am actually missing a thing right now because I can't write it as this, because there are, look, 1, 2, 3. There are a whole lot of a's, and there's only one a over here. So it's not just a. In fact, it's a to the p minus 1th power, since there are p minus 1 a's this list. So this is congruent to p minus 1 factorial modulo p, and my brain had finally worked out what exclamation mark is called. And we know that p minus 1 factorial is relatively prime to p, so we can divide p minus 1 factorial, and we have what a to the p minus 1's power is congruent to 1 modulo p, and it is the same as Fermat's little theorem. So that finished the proof, and we had a very tiny example, and we had also proved the little theorem. Now we're going to get to a big guy, and it's 1, 2, 3, 4, 5, 6, 7. I think it's 1,234,567. I think that's how you pronounce it, right? So we want to know if this is a prime number or not, and if we know that a to the 1,234,566 power is congruent to 899,557 modulo 1, 2, 3, 4, 5, 6, 7, then we know that it is not a prime number. It is not prime, because the Fermat's little theorem states that if 1, 2, 3, 4, 5, 6, 7 is a prime number, then this should be true, while in fact it is not true. It is totally not true. So 1, 2, 3, 4, 5, 6, 7 is not a prime number. Now you guys might be thinking, can we use this to identify if numbers are prime numbers or not? Yes, you can, but not always. So for example, the number 341. It can be divided by 11, and I'm going to do the division right now to show that it is not a prime number at all. So this number, 341, 2 to the 341th, 2 to the 341st power minus 1, it is a multiple of 341. Well, in fact, 341, as shown before, it is not a prime number. So you can use Fermat's little theorem in identifying primes, but it will not always work in the case of 341. And there's also a number where when it's this number 341, when it's 3, it says that it's not a prime number. And in fact, there's a bigger troublemaker. Yeah, there is another number where no matter what the a is, this number it is not a prime, but no matter what a is, the Fermat's theorem also always states that it is not a prime. So there are big troublemakers when you try to use Fermat's theorem upside down. So this will be as far as we'll cover today, and see you next time.